can you please give a very warm welcome to Richard Fitton, who's the research lead for Energy House Laboratories at the University of Salford. The floor is yours.
Thank you. Pardon me, sorry. So my name's Richard. I'm from the University of Salford, which is in Manchester. I was just casting my mind back. So I've been doing this role for about 10 years. And I wouldn't have done this talk about 10 years ago because our research group is around everything that is linked with houses and energy. And we're always on the house side of the energy meter. About 5 or 6 years ago, possibly a little bit longer, we stumbled into the areas of smart meters, and we've done a lot of work in that area since. And now there's just no gap between a house and the infrastructure. A V to G, V to H, smart meters, and all the other stuff, batteries and PV that goes with it. We could not ever now be a research group that just deals with houses. We're intrinsically linked with your sector, if you like. So it's I couldn't have done this 10 years ago, and I also had a full head of hair, and it was all black. But I'll give you a quick introduction to what we're doing. No, got it. So I'm the technical director of these facilities, basically. So we have the Energy House, we have the Thermal Measurement Laboratory, we have a Smart Meters and Smart Homes Lab, and last of all, we have the new facility, Energy House 2, which we'll spend a little bit of time on at the end. So Energy House is a very simple project. It's quite technological in its what it does, but it's a very simple thing. So Energy House is just a Victorian terrace in a huge environmental chamber. It's one of its kind in the world, and we've been busy ever since we opened that 10 years ago. So we started off doing a lot of retrofit work. Then so fabric insulation, air tightness, and the standard things that we do in fabric retrofit these days. Then we moved into smart. So everything then became smart. Smart controls, smart meters, EVs, and the various ways that they all interplay with the building itself. And we do a lot of large-scale field trials. So we work with the 3 biggest housing providers in the UK, and we do a lot of stuff out there in the field. Thermal Measurement Laboratory, very basic principle, we test insulation. So anything that we can put into insulate a building, we test in that laboratory. And the Smart Meters and Smart Homes Lab, that's probably one of our latest labs. And we look at a lot of things in there in terms of appliance disaggregation, smart meter and IoTs and how they connect, data analytics, and innovative uses for smart meter data. So what we do a lot of in that lab is taking smart meter data and IoT data, linking it, and then generating the energy performance of the building in which that meter sits. So we've done a lot of work in that area, and it's very interesting. It's something that government are exceptionally interested in at the moment. So this is Energy House 1. So we opened in 2011. We've done about £1.5 million of commercial income in there, plus a lot of grant-funded income as well. Like I say, there's a lot of work around retrofit, EVs, and building performance methodologies, and we've worked with the large players in the sector. So that is a success. That facility is deemed as a success. It's washed its face. It's done a lot of impact, and the funders, which was ERDF, we're absolutely delighted with it, and the university is very happy with what it does. So it's a very flexible facility. We can go down to -10 up to +30. We can put snow on the building. We can put sun on the building. It's in Manchester, so obviously we have to put rain on the building and wind as well. So it's a very, very physics-based approach to testing whatever we do in there. So we change the boiler, we do the same test. We change the insulation, we do the same test. It's a very, very experimentally based facility. So it's built exactly the same as you would find a normal building anywhere in the UK, basically. Solid brick walls, single glazed windows, suspended timber floors, pitch slate roof, etc. The bricks are 100 years old. It's exactly what it says it is. So why do we do all this? So we think that buildings are obviously a huge driver for energy in the UK and a huge contributor to climate change as well. So the stuff that we look at really is all around energy efficiency, the pathology of energy. So if we do something and it doesn't work, why doesn't it work? I think we can all say this project didn't work, but we need to know why it didn't. Smart energy systems, what we've all been talking about all day. I don't need to teach you guys about that. Electrification of heat and transport, which is a huge issue at the moment. Fuel poverty, which is an issue that doesn't get enough attention in my opinion. And rapid demonstrators and prototyping. So if we did a field trial for something like a boiler or a heating control or insulation, we'd usually have about 2 years in the field. So in Energy House 1, we can run through winter, spring, summer, autumn in about 2 or 3 weeks. So we can basically put a building through its paces in a very short period of time. It doesn't replace a field trial, but it tells us that the product technically works. And we also had other plans for that building as well. So in terms of live projects, we're doing a lot of work with Schneider around controls. We've got Homes and Energy Systems, which is looking at battery and PV installations and flexibility on the grid. We've got a large project called DEEP, which is funded by BEIS. So that's a £500,000 project. It's actually quite pertinent to what we're discussing in this room. So this is all about when we take that old building. We hear a lot of talk about Boris is going to push out all this money for air source heat pumps. Air source heat pumps will not work in a lot of buildings. It's as simple as that. They will not work in that building that I've just showed you. But when we insulate it, make it airtight, change the windows and doors and things like this, then basically, as part of that process, there's a tipping point, and it's about 2/3 of the way through that process. So we find out this is the point where that technology will work in that building. And that's the model that the government needs to look at. And we do large-scale testing of things like aging of insulation and things like that, and how that changes over the decades. And like I said, a very live project is looking at smart meter data to generate energy performance certificates, or something very similar to an energy performance certificate, which is very interesting to me anyway. So we do a lot of, we can rapidly put things together. So this project was called Haven. So Home as a virtual energy network. This is about putting multiple assets under control. So we had Tesla battery, we had the EV outside, we've got the Mixergy, kind of a smart hot water tank, and NEBI air source heat pump unit. And the challenge there was to get it all working together. It's actually very, very difficult. Tesla won't let you into any of their interfaces. NEBI have got a great API, but it doesn't talk to some other things. Mixergy's got their own, and Nissan has its own, which was locked up back then. So it's actually something very simple like this takes a hell of a lot of work, and if you were to do that in someone's house, they'd probably become quite frustrated with you trying to get things in there and the amount of wiring and stuff like that. So this is what we're all about, rapidly demonstrating these projects. So a typical example is a project that we did with Saint-Gobain. So Saint-Gobain's not a household name, but they're the biggest construction product manufacturer in the world. So they own British Gypsum, Celotex, Isover, Weber, all these different companies that are big names in the construction industry, shall we say. So what we did in that job is we took everything that we could put on the building, we put it all on, and then we take it off bit by bit. So you do underfloor insulation, loft insulation, external wall insulation, internal and external, draft proofing, new windows, etc., which is interesting anyway to see what global saving you get. But then you can split it down into what saved the most, what did the best, what was the best bang for your buck, and also what order you should do things in. So that total retrofit saved about 60% of energy. It took about £348 off a consumer's energy bill, and all these different things. And we got better thermal comfort in there. It's all been published, this report, done a few years ago. So it's really important that we can visualise this type of stuff and see what's saved where and what actually works. So Energy House 2, we had a few people kind of nipping at our heels. There was an outfit in South Korea, an outfit in Australia that was talking to us about, we're going to start a new facility. Would you like to help? Our answer was yes, we'll help. But so we got this kind of feeling that things were going to change. We could also see decarbonisation. This was going about 5 or 6 years ago. Was really starting to kind of pick up its feet. So we needed somewhere to grow, somewhere to work, somewhere to go a bit more international. We have a big footprint in the UK and EU, but we weren't doing anything on new build. All the stuff that we did was based around this retrofit, this old building, which is great for the UK. Everyone recognises that building. But you take it somewhere like Spain or even the States, and they have trouble understanding, and take it to Norway, they cannot understand why we live in buildings like this. And we needed a wider range of climates, and off-site construction at that time, 5 or 6 years ago, was again really picking up its feet, and it's found its feet now. That's really the only way forward in the built environment, we believe. So Energy House 2, as a principle, needed to be a lot bigger and better and more flexible. So we have deeper temperatures, -20 to +40, more wind, more rain, more solar radiation, and more snow. So we can simulate in there buildings from about 95% of the populated areas on the Earth. So the Arctic and the Antarctic aren't very well populated and things like that. So we simulate where people live, and we've got a pretty good coverage on that. So we also needed somewhere where we can say, we're going to actually build in this building. So the Energy House 1, that Victorian kind of 1.5 brick terrace, everything was brought down a corridor and built. So literally in wheelbarrows, and was built in a chamber. We couldn't do that with this place. So we needed somewhere where people can go in and build the buildings of the future. Whatever that is, we don't choose that. Our clients choose that, and government chooses that, and the construction products manufacturers choose that, and the architects. So we can basically take things in and build it. So we also needed to test new builds. We retrofitters, I think it's safe to say, has stalled a little bit in the UK. It may come back round, it may be air source, it may be hydrogen, it might be insulation, but it's not fully formed yet. And we've got Energy House 1, that'll always stay with us. It's our kind of baby, it's not going to go anywhere. But we needed somewhere where we could innovative methods, off-site, novel methods, 3D printing of buildings always gets mentioned and things like this. Somewhere where we can put buildings in there and improve them and make them better as well. So we also needed a better interplay with the stuff that we talked about today. So, grid connections, PV. We use PV, we replicate the DC signal that comes off a PV panel, put it through the inverters, because as we're simulating a hot sunny day in California with our solar radiation rigs and hot temperatures, we need to be able to throw that same solar input onto the building as well in terms of the grid. V to G, V to H, so the new build is big enough to do that in as well. And real world smart metering will be provided by an energy supplier as well. So it's bigger, better, and a bit more bolder. So this is a model. I spent most of my career dismissing models and saying that we should measure everything. That's kind of how I've done things, but we have to visualize it somehow. So we should have a video that plays. There we go. So there's no music or anything on this video. It's only 1 hour and 45 minutes long, you'll be glad to know as well. So this is a 3D model that I did of Energy House 2. So it's a £16 million build. It's just over the road from where our old asset was, about 1,050 square meters, 2 large chambers. So I've put a couple of trucks on there so you can get scale. But basically anything that can be moved by road in the UK can go through those doors and build. So any off-site construction. So we can look at different buildings from all around the world in there. So you get an idea of the shape, the scale, and the size of the building. So it's pretty big. There's it without a roof on. It will have a roof on. And there's the Energy House 1 just kind of dumped in there as a model for size. And you'll also see it's got cars put next to it. We don't see anymore, like it opened up with, that a car can be separated from a home anymore. It's part of a home. It's part of the heating system as far as I'm concerned as well, with air source heat pumps. So V to G and V to H. Now the way that a Nissan Leaf, and I can tell you this, I've got one, reacts in different temperatures when it's discharging and charging, is hugely different. So we have to be able to put the car next to the house to do the V to G and V to H, because it changes. If we're down at -20, that battery will act in a far more different way than if it was at +40. So like I say, we cover about 95% of the global housing population, and we can build whatever we like in these 2 chambers. So in there, we can simulate wind, rain, snow, and we can put it directly onto the building. When a wall becomes saturated and when a roof's got snow on it, it can have a big difference. So snow on a roof will insulate it for about 3 weeks. Then as it turns to ice, it will start to conduct heat out of the building and become something that's quite bad for the building. So we need to look at all these conditions from all around the globe. But again, wind, rain, and snow will affect the way a car charges and discharges as well. So all interesting things for the full ecosystem of things that will be in there. So that's an idea of scale, shape, and size of the building. So as we just come round here now, it should change. So we've been offered a lot of things for this building because it's so big. So a lot of people want to look at EVs, how they charge and discharge, the thermal comfort of EVs. The caravan market, believe it or not, is a huge sector which is practically unregulated in terms of thermal comfort and heat. And there's a huge demand for using that chamber. So I don't like models. So this is it. And this is it about 2 weeks ago. So it's a huge black box. The architects love it. I'm not bothered what it looks like because it's the chamber that kind of does it for me. So we got this huge sprawling building right in the middle of campus. It will be finished in December this year. So where we're at the moment is the building's done. The inside of the building is more or less done, and what they're putting in now is a HVAC. So the HVAC is just £6 million alone, just for the cooling equipment and the heating equipment to keep that chamber either hot or cold. And it keeps it hot or cold to 0.5 of a degree. So if you speak to anyone about environmental chambers in the dairy sector or meat products, it's unheard of that such a large chamber is conditioned to that extent. But it gives us this test bed where we can look at whatever we want, when we want. It can be whatever measure temperature is outside, and we can change it inside. So this is taken from a drone. So we have a quick fly around here. But this basically gives you an idea of shape and size of the building. The pits are currently filled with soil. We can fill them with water, should we wish, and replicate flooding in there and how buildings react with a very dynamic environment that we're going to get in the next 10 or 15 years. And this is just a quick shot of inside, looking at the M&E service it installs for this building. So this is due to be starting commissioned in about 3 weeks' time. So yeah, in November, we should probably be expecting some kind of very cold weather and snow in there, which coincides with the very cold weather and snow in Manchester. So you could see that a bit of a waste of time, but hopefully we'll get to use it. So there's the web address and everything else, and a Twitter and a phone number and all that if anyone needs it. So that's what we do. We test buildings. We look at how they perform. We do it in the field. We do it in chambers. We do it in laboratories.
Richard, thank you so much for that. That was a brilliant presentation, and the work that is going on at Salford University is just astonishing. Thank you so much. I think we should show our appreciation for what